you would be taking down an image and then making an image level decision or image level classification problem over there. But here we are changing and we are making a pixel to pixel level, or every single sample over there is what is getting classified. So in semantic segmentation, typically what happens is something like this. So say I have an image over here. This is X. It goes into a segmentation process, and then out comes this kind of a thing where you have two different kind of classes of objects present over there, omega 0 and omega 1. Now these are essentially every pixel over there. So if this has n number of columns and m number of rows, then this would also be having the same n number of columns and m number of rows present over here. So this is what typically a semantic segmentation process is known to. Now, how we achieve? So semantic segmentation is a simple segmentation task. Okay. Now, how we end up achieving this kind of a semantic segmentation over here is by using convolutional operations. Okay. So let me get you an idea about how this works out. So say I have this X as my input, and I write this as, and this is color image. So this is 3 cross number of rows, which is m, into number of columns, which is n. Okay. Now this goes into a CNN block. So there is a conv block. Say this conv block is defined by some number of channels, or say 2C. This does a 3 cross 3 convolution operations. It does it with a stride of 1 and with the padding of and also with the padding of 1. So this is going to produce me some output tensor, which is y predict. So this y is going to belong to 2 cross. So what will be the size of y? Is definitely 2 channels, because in the convolution you had 2 channels. And then what will be the remaining part over there?
M cross n, sir.
2 cross m cross n. Okay. Now if you look over here, the spatial size of x and y are the same. This is what turns out to be over here. Now the point is, now that the spatial size of x and y both are m cross n and they are the same, this works out good. Now what comes out next is something like this. So you get a 2-channel output over here. Okay. So your y belongs to r power of 2 cross m cross n. This is what it belongs to. So there would essentially be 2 such channels which get shown. So let us look into the first channel. So this is essentially for, if this is how the object is. So this is going to represent omega 0. So if that is omega 0, then all pixels, so let me write it. All pixels belonging to omega 0 is white, and over here, which belongs to omega 1, you will have the converse. So the shaded regions are black. And if this is for omega 1, then essentially all pixel belonging to omega 1 is white. This is what would come out over here.
Hello, sir.
Yeah.
Sir, can you please repeat that omega 0 and omega 1 part?
Okay. So look over here. What did we say? I want to do a simple segmentation task where this outside region has the class label of omega 0. The inside within this blob has a class label of omega 1. Okay. So now if the outside region has omega 0 as a class label and inside one has omega 1 as a class label, so here when I'm getting this output being created over here, that it is a 2-channel output, I would like to see in each of these channels. Okay. Now the first channel is what I denote as that belonging to omega 1 or the first class. So in that case, all the pixels, so let's see which pixels were omega 1. So all of these outside the blob pixels were omega 1. So those pixels are supposed to be 1 with
Sir,
a value.
outside were omega 0, right, sir?
Sorry, omega 0. Yes, that's what I'm saying. Omega. So in the segmentation, you wanted to have a 0-1 map. I am slicing it out. Okay. So let me wait. Let me give you this example with 3 classes, then you will understand.
Okay.
So say I have 3 classes of objects in this X. So there is an apple and there is a square. Okay, let me make this as red, and there is a green square. Great. So this is the background, which is omega 0. This is apple, which is omega 1. This is square, which is omega 2. So now if this is the scenario over here, that you have omega 0, omega 1 and omega 2, which is present over here, then let us see how it works out. So when I have this is what you have. So in case of omega 0, okay. In case of omega 1, And in case of omega 2, this is what it looks like.
Okay, so this is what we mean by dividing the images into blocks, right? Like,
This is what I did not get it.
so like we are dividing them, like segmenting them, or like into blocks, right? So like omega 1, omega 2, and
Into segments. Into
into
segments.
okay, understood.
Okay. So each of these is a map. So this is a map of a certain class of segments. Each of this is a map of a certain class of segments. Okay. So now the point is that there are this class of problems are a lot of them, and there are some very popular examples. So one of those examples of semantic segmentation. So say let us take example uses of semantic segmentation. One is in autonomous driving. So you need to segment the street view videos to easily identify objects. Then there are like examples in digital media industry. Where you can do photo morphing, then character recasting. So character recasting, has anybody seen like how the movie Avatar was made? Or any of the current generation of these animated movies from Pixar or Disney which come out? Has anybody seen like behind the scenes of how they are made actually? No idea.
Sir, I think
Sir,
the
CGI put
Yeah, CGI is computer generated imagery. So in fact, like when we will get into adversarial learning, I will show you one of the most popular things which people know is generative adversarial networks or GANs. So GANs are these days what are taking on the whole CGI world with a storm. I mean, they have already done. I mean, there are full scale movies which are produced with generative adversarial networks. But the point is like, I'm not speaking about computer generated imagery. I'm speaking about the other, which is essentially called as your character morphing.
sir, I think the real people wear some kind of costumes and then they do the actions that are performed in the movies, and then they like kind of make the characters as the person.
Yep, yep. Okay, great. So that's essentially what you do. So you need a lot of, so because these people are wearing those costumes, and so you might also be seeing the green screen effect. Let me use this green screen production. Green screen production is uh, so there was this interesting sort of like a documentary from a self-made movie maker from one of the Mumbai backward areas. most likely Dombivli. So the thing on YouTube was called as Dombivli ka Superman or something of that sort. So there he was showing exactly. So what this guy was doing is that he would go around with the camera, first make like real crazy shoots over there, and then he would reconstruct himself as flying and something, and that is with a green screen. So the idea over there is that you have a background which is essentially fully green, which does not intrude with anybody's natural characters. I mean, none of us are essentially Shrek or somebody else of that sort. So we are not green in color. And then you can very easily segment out the human in front of it. So today, when you turn on virtual backgrounds on your, in fact, I don't know, should be having the virtual background over here, right? Let me see. Then it becomes easy. I can show you. Anybody has any idea on how to turn on that virtual background in MS Teams?
Sir, before we join, there is an option.
After I join, I don't get
So
an
if
option.
you click on the three dots and then apply background effect.
Let me see. Okay, I'm not getting it, most likely because I'm joined from the browser since my desktop app was not letting me connect.
Yes,
So
sir,
you
it's
can,
only available in the app.
so
It's
you can
available only in the desktop version, right? Huh. Okay.
open over
So
the
you know
video.
about virtual background. So typically, and for virtual backgrounds to work out good, I mean, instead of this cluttered background as I have, I mean, this is not a virtual background. This is actually a real bookshelf over there. A lot of people mistake that one. So you would actually need a green screen being put down, and that works out pretty fine. I mean, in the earlier days, so now there are a lot of actual deep learning algorithms which get deployed in order to do it. But earlier there used to be these kind of green screen production systems which we are putting into play. Okay, so that's about where they go to use, and a very important case is the region on which I work. So that's on digital health. And this is with medical image analysis. So you need to run a lot of segmentations in terms of carving out organs in order to measure their dimensions, shape, size, and then come down to certain attributes about the disease, or say certain things about the diagnosis quality and everything. Or if you want to make some plans for pre-operation on like how will you actually run an operation, so pre-operative planning, that is also something where you need this kind of a semantic segmentation going. There are several. So you have its use in earth and climate sciences, etc. So earth and climate sciences has in a sense that you can run these semantic segmentations in order to find out what is the land usage pattern from satellite images, and that helps you understand whether the forest cover or the land use pattern, which is like some place which was earlier a forest, has been turned to an agrarian land, and agrarian land has been turned to a residential land, or a residential land got reclaimed back into forest land, or like a residential plot or a land just got deserted out because it ran out of water. So whether it's converting and there is desertification happening. So this helps a lot for climate and earth scientists to really go and understand that we have a sustainable planet, and they make use of significant amount of these kind of tools in order to do that. So this is for land use analysis from satellite images. And there are several. So in fact, this does not restrict itself to images in any way. So I mean, now I do work with people who do it on signals, and I know that extensively any of these methods can be applied on signals, on 1D signals, on multi-dimensional signals, or multi-channel 1D signals as well, something like multi-channel ECG, or an ECG and an EEG co-recorded signal space as well. So just give me a minute. I need to get some water. Okay. So one of these very powerful examples which I would be speaking about is what is called as UNet. Okay. So what this UNet does is essentially something of this sort. So you have a set of convolutional operations which in some way mimic the filter banking kind of a strategy which happens in BGG, and then you keep on completing this one. So the example works out like this. So essentially you have an input image which is X, which goes over here, and this has a specific size in how you put down over there. So I'm just going to write down exactly how it works out. So I'm representing in a strategic way along the plane over there. So the input is say this can be in general we consider this as a 1 cross 572 cross 572. Okay, now from here it undergoes a convolution operation. So we'll define what this convolution operation is in order to produce an output over here which is 64 cross 570 cross 570. Okay, and then again it so we'll define what is over here, and after this convolution it produces what is called as again 64 cross 568 cross 568. Okay, now can you help me in writing down what is this convolution operator going to look like? It's a 2D convolution operator. So can somebody help me in defining what that 2D convolution operator is going to be? The first 2D convolution operator, which is present over here.
Sir, 64C. 3W 1S0P.
64C 3W 1S
0P.
1S0P. So will that work out? Yeah, I think it will work out. Yeah. So what will be for the next one?
So it could be same.
64C 3W 1S0P. Okay. Now, once the output comes out from here, the next task is you run into a max pooling operation such that now here you get down a 64 cross 284 cross 284. Okay. So if I do that, what will be the max pool factor? What will be this max pool layer definition as well? So can you tell me what will be the max pool layer definition as well over here?
(2W2S).
It's 2W2S. Okay, great. Now from here, I again have convolution layers, and then I get this output. Now here, what I get is 128 cross 282 cross 282, and here I get down again 128 cross 280 cross 280. So what would that make this convolution operator as, and what will be this convolution operator as?
128C 3W10.
So this is what it comes to, and then it keeps on going. Okay, so in order to make it simple, what I'm going to do is I will just copy that image. Awesome. It does not give me a paste option. Let me do an image search. No, I can copy image address and paste it. It. Okay, so now essentially you would see that you end up getting this kind of a structure, which is what is called as a unit. Now it gets its name from the fact that this resembles a U structure. So this looks like a U. That's why they used to call it UNet. There are also a lot of other things from the inventors. One of them said that because they keep on doing successive unification. So I'll tell you what that successive unification is. So what they're doing over here is that you can think of this complete structure as some sort of an encoder, and this part of it as some sort of a thing called as a decoder. Okay, and they are pretty much symmetric. So at every level, you do a max pooling, you go till here. So till here is what I have shown over here. You again do a max pooling. This is again by a 2x2 max pooling. So 2W2S. You again run it over here, but here the number of channels are increasing. Now, if you carefully look into it, so what it is doing is that it doubles the number of channel and it decreases the spatial span also into half. So each of the spatial span sizes are decreasing by half, and it's doubling the number of channels. And that's how it keeps on going. So it did the same thing. So you had a 280, which became 140 cross 140 because of a max pooling. Then from here, it goes to get 256 channels. So it's a 256C. So let me write it down. So this operation is 256C 3W1S 0P. Okay, and the output essentially then comes out as 138 cross 138. Similarly, this is also the same. That's why you get down a 136. Wow. Just a minute. My pen stopped working. No, it is working. So now here this becomes 136 in the spatial span. Then what you do is you again do a max pooling. You bring it to 68 cross 68. Then you do a convolution, and this convolution over here is 512C 3W1S 0P. The same holds over here, and that brings it to 64 cross 64. You do a max pooling over here, and you get a 32 cross 32. Then you run into a convolution, which is essentially 1024C 3W 1S 0P. Okay, you do that for this convolution layer as well. So now here you are left with a tensor size of spatial span 28 cross 28 and 1024 channels. Now this is something interesting which will happen over here. So what I do is I have 1024 channels over here. I take all the 1024 channels which come from here. Just a minute. Is it right? Oh, no. Just hold on. That has to be 5112. So this convolution kernel over here is something which reduces. So this one is a 512C 3W 1S 0P. So essentially what you did is you got 512 channels over here. Then after the up convolution by 2 cross 2. So this no. Wait. This is the same, but this new function over here, which you define as upconv, if you look over here. Okay. Now I'll come to what is an up convolution operation. This is something which we called as a deconvolution or a convolution with resampling operation, which comes over here. Now that is something what it would do is that it can help you reclaim your spatial span. So you can essentially make it 4 times by reducing and in the way that you are essentially making it 4 times over there. So you're reducing the number of channels as well. So that is something which happens over there. So I will explain in details exactly how that operation works, but later on. Right now, not. So here you get 512 channels. Now what you do is you take these 512 channels from here onto here with a clever trick. The trick is that the spatial span over here is 56 cross 56. Okay. Now, when you take something from here, you will not be able to take 64 cross 64. You will have to chunk this inner part of 56 cross 56. That's the reason why you see a dotted small blob over here, which is essentially getting chunked. What you do is you take it from here, you concatenate it over here. Now you have 512 channels which came from this side. You have 512 channels which came from this side. Together you have 1024 channels. Now after that, you run them through a standard or 2D convolution operator. And this 2D convolution operator over here is the same as this particular operator. So you still have 512 channels over there on which you are doing it now. You would see that this convolution operator is also 512 channels on which you are doing. Then you again have this kind of a up convolution with the 2 cross 2 factor. Now as a result of which what you will do is you will reduce the number of channels which comes from. So here you get 256 channels which comes from here. You take another 256 channels and concatenate it over here, and that comes from this matched layer. The only difference is that you will have to chunk out only this core part of 104 cross 104 instead of the 136 cross 136 over here. So then you get this 512 channels very clearly. You again run convolutions which are of a symmetric order. So that's 256 channels and with 3 cross 3. So that is what you are going to run. So similarly, you come over here, then you get your 2 cross 2 up convolution operation working, and that will get you 128 channels over here. So these are 128 channels which come over here. You have another 128 channels and you are chunking in this inner core, which is of 200 cross 200. So this inner core of 200 cross 200 is what gets placed over here. There are 128 channels which came from here, 128 channels which came from here. That makes it 256 channels. You push it through. Okay. Now this convolution operation is the same as this convolution operations itself, and that is with 128 C. So let me write down 128C, 3W, 1S, 0P. That is this one, this one, this one, and this one. Okay. Now you again run it through a 2x2 up convolution over here, and then again put it down as 64C, 3W, 1S, 0P. Which comes out over here, and then finally you put another 2x2 convolution coming down over here. No, sorry, that will be the 1x1 convolution. So this one over here is this 1x1 convolution. So the whole purpose is that from 64 channels, you don't want to compromise anything on the spatial span, but you want to sandwich them onto 2 channels. That was the purpose of having this 1x1 convolution, which is present over here. So this was about the forward pass of a unit. So essentially what you get is that your input image is something like 1 cross 572 cross 572, and your output over here becomes 2 cross 388 cross 388. So definitely you did lose out something on the spatial span, but you did not lose out significantly over there. So there was somewhat reduction in the spatial span, but then if you're just taking only the middle part of it, then it works out. Now, definitely, if you would have used padding in an appropriate manner, these were all with 0 paddings. But if you had appropriate amount of padding being added, then you could have actually tackled this vanishing boundary case as well. So you don't need to really worry that the boundary got vanished off completely. We could have tackled that as well. So now the next part comes. This is just the forward pass, but then how do you train is the interesting question. So that is something which I'm going to take on in tomorrow's class, where I will explain the whole training process, including like how these gradients are going to flow and what is the need for these kind of concatenation layers, which also plays a significant part. Now, not only concatenation is one of these operations, so there would be a much simpler one, which is called as segnet, which I would show you. It does not use any of those, but it just uses an encoder-decoder like structure in order to do it. And eventually I will show you something which came up from our group called as SUMNet, which was a merging of the segnet principles and the unit, and gave a much computationally lightweight and very powerful model to solve it out as well. Okay, so any doubts still here? Let us discuss on that, and I will start with the training part tomorrow.
Hello, sir. Vaibhav, this is
Yeah,
sir. What is the operation of up convolution? What does it do?
I will come to it. I will come to it. So just hold on for now. Tomorrow I'm going to actually show you what an up convolution works like. Okay. It will take me some more time. It will take me about 30 minutes or so to explain you. Okay, if there are no questions, then let us close for the day, and tomorrow we start from this point.
So what is the use for this Sir,
What is the use for what?
so what is the use of this this cross connection from the previous slide? This gray arrow, no?
Tomorrow.
I mean,
There is an importance of
why
this
is it
one.
used? Tomorrow.
That we will discuss tomorrow. I have not yet finished it off. That's what I said. Tomorrow, when I explain you the training process,
Okay.
I will explain you exactly what is the need for this concatenation which is happening.
Hello, sir.
Yes.
Sir, like regarding the segmentation example, where you had just shown that background apple and square image, like sir, after that you discussed that it also finds its application in medical image analysis domain, right, sir? Now, sir, like for example, we have an MRI image like with a black background and some and the brain image in front. Like, does the segmentation process works in that way? Like we can separate like some omega 1 and omega 0, and that omega 1 separates out that brain. Like, does that happen in that way? Like,
Yes. So typical examples are tumor segmentation. So if you're looking at, so what kind of MR, abdominal or neuro, are you looking at?
neuro, sir.
Neuro. So a typical case on which we work is for brain lesion segmentations and stroke lesion segmentation. So you have essentially two different types of lesions, or the lesion is the damaged part of the tissue, but there are two different types of tissues. One is called as the core, which is a non-salvageable, so you cannot treat and recover the neurons from there. But the other is what is called as the penumbra, which is the salvageable part. So essentially the neurons are not yet dead, but they are physiologically sort of incapacitated to do some work, so you can still recover the functionality of those neurons. Now, what is very important is for the surgeons to find out what is the core and penumbra before they actually take the knife to do anything. And even for neuromedicine specialists who actually give a therapeutic drug in order to recover, they need to find out, do this dosage estimation. So a dosage estimation is done based on what is the size of the overall tumor and what is the ratio, plus what is the granularity of the core and penumbra. So that's where these things come off immense help. And at least for the core penumbra segmentation for regional analysis task, it's a multi-sequence MR which goes in. So it's not always a T1 or a T2 which will do. So you get down a T1, T1C, a T2, a DWI, a PWI, sometimes even spin sequences. Everything go down together. So it's, I mean, one of the like maximum sequence I've seen is 7 sequences. So all 7 sequences taken together, they are pushed into the network in order to get it done.
Okay, sir. So I mean, like we can use these things, right, sir?
Yeah, I mean, there are very standard examples. Just go and look into the current publications with Brat's challenge and you will find them.
Okay. And sir, one more thing, like in the initially when we were taught like 1x1 convolution,